So we left off at example 7, part B. So those of you that were just writing it down yesterday, you did example 7. It looked like this, okay, about picking 4 out of the 20 songs from your MP3 player, okay? So this is part B of that. So it says a raffle at a school carnival awards prizes of $100, $50, $25, and $10. If 25 raffle tickets are sold, how many different ways can the prizes be distributed? Okay. So first of all, what's the total number of objects we're choosing from? No, not 4. 25 raffle tickets have been purchased in total, right? How many are we picking? 4 of them. Is it a combination or a permutation? You guys decide in your group. So permutation, because order matters because of the distinct different values of the prize. If it was $400 prizes, you combination people, you would have been correct. Then we would have used a combination. Okay. So we have 25 raffle tickets that were sold. Is that right? Yeah. We're picking 4 winners, but we're going to use a permutation instead of a combination because the 4 winners have different values that they obtain. So it's different for me if I'm picked as the winner of 100 than if I'm picked as the winner of 10. Okay? All right, so this calculation, here's what I would expect you to know about this formula. I would expect you to know and be able to write on your paper to show work that the formula looks like this. But then I would let you take your calculator and type in 25P4 and get the answer that way. Does that make sense? Okay, so work would be represented with this right here, but you don't have to write out all the factorials. Now, don't take that as you don't have to know what a factorial is, because you know I will ask you a question that will require you to know something about factorials, even if you can't put it in a calculator. Okay? So 303,600 ways to pick those 4 raffle winners. And there would be significantly less ways if the prizes weren't different, right? Because then the order wouldn't matter, and we'd divide by that extra 4 factorial. Okay? It's all right with everybody? Okay. All right. How many diagonals does a regular octagon have? I feel like our class is basically like a puzzle class right now. Like we just put up a new problem, and it's like a new puzzle for us to figure out, right? Okay, so how many diagonals does a regular octagon have? 4. Okay, so diagonal goes from, so what is a diagonal? You guys don't remember? From point to point through the, okay, so like that would be a diagonal, right? Okay. So we could either start drawing all the diagonals, right? Let's say we started at this vertex. How many diagonals can you draw from that vertex? 1, 2, 3, 4, 5. Okay. Okay. We're not going to count these 2, right? Because these 2 aren't technically diagonals because they're sides of the object, right? All right. So we count all of those. 1, 2, 3, 4, 5. Okay. Then we'd want to go and we want to count all the ones from the next vertex. Okay? And then there would be 1, 2, 3, 4, 5. Because those ones didn't touch each other, right? Then I'd want to go count all the ones from this vertex. Guess how many there would be? 4. Good, because I wouldn't want to overlap the one that I already counted, right? Okay. So let's say I want a faster way to count this, right? I can use combinations or permutations to count this, but I have to know which one. I have to know the total and what I'm choosing. And this problem has a little twist on it, which is why we included it. I know, all these little twists. You guys aren't going to like them. All right. So basically, a diagonal connects vertex to vertex, right? How many vertices are there in total in an octagon? 8. So there are 8 in total. And when you draw a diagonal, how many are you using? When you draw one diagonal, how many vertices are you using? 2. So every time I pick a diagonal, I am picking 2 points to connect out of my 8 points total. Okay, then the question becomes, is it a permutation or is it a combination? So think for a minute and decide in your mind. Don't let it out. Okay. So you're deciding, does order matter? If yes, then permutation. If not, combination. Okay, if you're still having trouble deciding if order matters, think about if the group has already been selected. Okay, so like, oh, congratulations, you 2 vertices have been selected. Okay, to be connected. Whoosh. Okay, so that's the diagonal I'm counting. Is it a different diagonal if I picked those vertices in a different order? No. Okay, so does order matter? No. Okay, so it mattered in the raffle problem because when we picked 4 people, they each got a different prize if they were picked in a different position, right? So order mattered. Here, when I pick the 2 vertices, it doesn't matter which one I pick first or second. They're both just part of that one diagonal. If I count this, if order did matter, I would count, let's call this vertex 1, 2, 3, 4, to vertex 4. This means 1, 4 would be a different choice than 4, 1. But we're counting diagonals. Is that a different diagonal? No. So I don't want to count this twice, so order doesn't matter. So I want to use my combination. Okay? So we can do 8, choose 2. Okay, that's how they say it. And the calculation for this, little reminder, would be like this. Okay. Which this one actually isn't that hard to calculate because 8 minus 2 factorial is 6 factorial. And I promised Jenny, she asked me a good question yesterday. I'm going to make a note about this. Is 6 factorial times 2 factorial the same thing as 12 factorial? No. 12 factorial is like a gigantic number, right? And though this number is a little bit gigantic, it's not as gigantic as 12 factorial. Okay, doing 6 times 5 times 4 times 3 times 2 times 1 times 2 times 1 is not as big as doing 12 times 11 times 10 times 9 times 8 times 7. See how those would be much different? Okay, so you can't combine any factorials just together using any sort of operations. But the 8 factorial and the 6 factorial, when they canceled each other out, what would be left where? What would be left? So 8 is bigger than 6. So 8 times 7, and then everything from 6 down would have canceled out with this, right? So this really isn't that bad. This is really 56 being divided by 2, which is 28. Now that's actually not the answer. Sorry. It's the answer to this, but this actually isn't the entire answer to the problem because you guys laughed at Eric earlier, but what he did is exactly why we have to pay a little extra attention in this problem. When we said from any of the 8 vertices, you can choose any 2 of them, yes, that counted all the diagonals, but it also counted something else. What else did it count besides the diagonals? Raven? Yeah, it also counted all of this. Okay. Oops. Right? So what this means is 28 represents, if I connect all the diagonals and count them all as I go without overlapping them, plus the sides of the polygon, that's a total of 28. Any way you can connect 2 points from that polygon. Okay? Sure. All right. So what we need to do here is we just counted some extra stuff. How many things extra did we count? 8, because it's an octagon, so I just got to take off the sides. Okay? So the final answer is actually going to be 20 because we accidentally counted the 8 sides. Okay? Because a combination can't really distinguish between diagonals and sides of a polygon. We have to do that for it, and this is why probability is hard. These formulas give you a way to quickly count stuff, but you have to arrange the counting of the objects, so it requires you to do the thinking about the scenario. Okay? All right. I'm going to give your group a little time to go through and try some different tasks. Okay? And in the tasks, you're going to do them all, and then we're going to go through and correct them all, and I'm not going to lie. Some of them you totally have the skills to do, and some of them, unless you do some deep thinking, are a little bit tricky and some special circumstances that we have to look at again. Jenny?
So, I just have a question with the...
Sure.
How would you avoid getting that, like, those extra 8?
There's no way for me to avoid getting it using a combination. If I counted them by hand, I could avoid getting the 8. But then the problem is, let's say they didn't do like an octagon. Say they did an object much larger, something we wouldn't draw. Let's say they said like, oh, if there's a 100-sided polygon or something and you wanted to draw the diagonals, how many are there? You wouldn't sit there and count it. So this is going to give you a much faster way to count it. So you would do this, but you would have to have the logic and the critical thinking skill to subtract then the 100 sides from it that you didn't mean to count. Does that make sense? Okay. All right. So, here we. All right. So we're about. Oh yeah. Sorry. Other answer. Go for it.
We did 10 factorial plus 1 because the possibility is like 10 to the 5.
Okay. So none of you are exactly right. Okay. But you all bring forward good points. Okay. 1, it's not infinite because you can only arrange the beads so many ways. 2, Julia's right. The clasp is always in one place. But so here's the thing. When you put a bracelet on, it is circular, which brought forward your idea of infinite, right? He's pulling this infinite idea from these circular objects. So that is a harder thing to arrange than being a linear combination, which goes back to Eric's question about this being a line, no matter what shape it is, right? Okay, unless, like I said, they randomly let other people go first or something. Even if they loop their line around your Disneyland, whatever, right? Okay, then 7 people are in line, 1, 2, 3, 4, 5, 6, 7. So first of all, part E wasn't any different than what we've done before. Okay? All right? Now, A is a bracelet. Bracelets are technically circular, but this bracelet has a clasp. So we're not going to do what Julia did and add 1 to it. However, the clasp is extremely important in the fact that it's not going to change location. So what it does for us is instead of the circle being this infinite thing that we don't know where the beginning is, we know where the beginning is, but we don't count the clasp as something because all it does for us is identify the beginning, right? So then even though you wear a bracelet like a circle, this bracelet, because we could think about unclasping it and holding it out, it actually is like a line because the clasp represents where the beginning of the line is going to line up. So in part A, you would do 10 factorial, but. Okay? This counts lining up the beads like here's bead number 1, bead number 2, whatever, all the way down to bead number 10. And I count the beads in another order like 10 and then 9 and then 8 all the way down to 1. That counts these as 2 different arrangements, correct? But because a bracelet is strung together on a string, we would argue that these are actually the same arrangement if I held the bracelet like this and then went like this. Did I have to rearrange the beads to get that new order? No. So some permutations are reflective, meaning if I just look at it from the other way, it's the same exact thing. So really, I've double counted every option, right? Like 1 through 10 is really the same as 10 through 1. And so the way we do this is we just take this and divide by 2. And this is because it can technically be called reflective. All right. Okay. All right. Part B. A basketball huddle of 5 players. Okay? Matt.
Infinite.
No. We cannot move them all around the court. We're just talking about the number of ways to arrange the 5 players. Raven. Okay, so smart idea. Okay, close. We actually don't divide this 1 by 2 because dividing it by 2 was because I could flip it over and see the reflection. Hi, basketball player. Right? Not going to happen. And is he going to look the same from the other side? No. Okay. The beads are a little bit different, all right, a little more flexible. So no reflections with people. Eric, and then I'll come back to you. Yes, but we don't normally write it that way. Good. Okay, So what we normally think about it is this. Okay, so what? Why would I subtract 1? What is the difference between the bracelet that had a clasp? Okay, we already talked about why we didn't do this, right? Okay, if the bracelet wasn't reflective, it was just a basic 10 factorial idea, right? Why is the huddle of people not a basic 5 factorial idea? Jonathan. Okay, because it's a circle. And is there a distinct beginning? Like, do they have a clasp? So is there anything that signifies to me, oh, it's starting right here? Right. So I have to take basically one of the people and call them the start, right? Like if I'm going to tell you, oh, here's how they huddled up, you're going to be like, well, who was where? I have to say like, oh, start with so-and-so, right? So if I say start with so-and-so, I've taken one of the players out of the ability of like choices to order them. Okay? So basically when something's in a circle and there's nothing in the circle that signifies it starts after this, you have to subtract one of the options off because one of them has to be the distinct beginning. Okay? So like we're all huddled in a circle, right? There's nothing here to signify the beginning. Then I have to say like, oh, if you start with Claire, you could arrange, and that immediately takes one of them off and only is allowing me to arrange 4 people, okay, instead of 5. The bracelet with the clasp was different because the clasp, which is why we didn't count it, because it's not actually a way to arrange the beads, but I didn't have to subtract one of the beads because the clasp gave me a place to start my counting, and I didn't have to use one of the beads as the starting place, okay? All right, so let's skip down to F, okay? Now that we've talked about bracelets a little bit, okay? So F, 6 charms on a bracelet with no clasp. So you have a bracelet. This time it has no clasp. Monet. So that part is true. It doesn't have a distinct beginning, so we have to do that. But there's also something we're missing. It's a bracelet. Okay? What happened with our other bracelet? It was reflective, right? You could just flip it over and see them in a different order. So divide that option by 2. Min Xiao? Right. 6 nickels in a circle on a table.
It's not infinity.
Okay, it's not infinity.
But it is 6 factorial times 2.
Times 2? Why times 2?
Because you can flip the nickels over and it'd be a different side.
Okay, and it would be a different side. All that means is we don't divide it by 2. We don't reflect it. Okay? And the 6 nickels in a circle, is there a distinct beginning? No. So we have to get rid of one of those nickels to call it the beginning. Okay? Feeling a little bit better? Okay. No. Okay. No times 2. Because that means you're counting like all of a sudden more nickels. Okay? You're not going to do the opposite of dividing by 2. The dividing by 2 was, the options are the same. So when I list them all out, half of them are really the same as the other if I flip it over. So get rid of half of them. But I'm not going to double what I counted. It would be impossible for me to double it without more nickels. Okay? All right, that leaves us with part D. 8 pizza toppings placed on a revolving tray. Somebody new. What do we think? Julia. Good. Okay, why the -1? There's no distinct beginning. So basically you have to say like, oh, from the pepper, like something is going to have to be called the beginning. So you're really only arranging 7 things around the beginning. Why not divide it by 2 and say, oh, really? You can just flip it over and see the arrangements the other way. All the toppings are going to fall off, right? It's physically talking about flipping it over. So like people don't work, okay? The nickels don't work because they physically look different on the back. The pizza toppings don't work because, one, you're just going to see the back side of the tray. You're not actually going to see the toppings unless you have a see-through tray, but then all the toppings would have fallen off. Okay? All right? So, yeah. Okay? So there's a realistic thing going on here. Jenny. All right. So we're going to build a committee. When you hear the word committee, what pops into your head? Combination. Just a group, right? Does the order matter in the group? No. Okay, so combinations. There's 8 freshmen and 10 sophomores, so how would we build the group? So I just want to look at B and C. Shh, you guys, please, let other people hear. If you're going to clean your stuff up, do it so I don't hear it. Okay. If I'm building a group that's all sophomores, okay, it's a combination because it's a committee, okay, and 5 members are being picked, okay? If they've already said it's all sophomores, what's the total of number of students I can choose from? 10, because there's only 10 sophomores. And how many people are going to be on my committee? Okay. And you would do that calculation. Okay. Now, if they say the committee can consist of 1 freshman and 4 sophomores, this is actually 2 different decisions, right? First, you're going to go and choose your 1 freshman. Then you're going to go and you're going to choose your 4 sophomores. So this is going to be 8 choose 1, and this is going to be 10 choose 4. Now what to do with those 2 numbers? No. Multiply them. Here's why. This is like the tree, okay? This gives you the number of ways that you can pick that 1 freshman. So here's all those different ways. But that 1 freshman can be paired up with any of these groups of sophomores. So it would have all these branches coming off here. And this would have all these branches coming off here. So because any of these can be paired with any of these, it's like the counting principle. To count it faster, you just multiply the 2 numbers together. Okay? Your homework tonight can be done with what we did yesterday. But we have to keep thinking about these different things because when we move further into probability, it's going to get more difficult.